Hello everyone. On this video we will be going over a few applications involving double integrals. Okay, so to get started we're going to have a quick explanation of mass, which is just the measure of a body's resistance to change in motion. Resistance to change in motion. Okay. Now, the one thing we know about mass is that it's independent of any gravitational systems. Okay, especially where that body is located. So the mass of an object on Earth would have the same mass on the moon, even though the gravitational systems are different. Okay, so mass is not the weight; it's the actual mass of the object. Okay, now density, on the other hand, is the measure of mass per unit of volume. Measure of mass per unit of volume. Okay. So, for example, if you have grams per cubic centimeter, okay, and here we're going to denote the density by rho, which kind of looks like a lowercase p. Clean up that little. All right, so one of the formulas for mass, you do have mass is equal to force divided by acceleration, but since we're using double integrals, we're not looking at that formula. We're looking at the formula for mass equal density times the area. Okay, which, of course, our density is our rho, and our area is the integral between a and b, f of x minus g of x with respect to x. Okay, so one of the formulas for mass is rho times the area. Okay, now when you look at another term that we'll call the planar lamina or lamina, I don't know how it's pronounced, but take your pick. You have the planar lamina, that considers density to be a measure of mass per unit of area. So that looks at density as a measure of mass per unit of area. All right, so we're going to go ahead and draw a little two-dimensional graph to kind of help explain it. So if you have your XY axis, X and your Y, let's say you have your unit of mass here. Okay, so let's say we just pick one rectangle of this unit of mass. Pick the center points of that rectangle. Okay, so let's say it's bounded on the left by some value A and on the right by some value of B. But this middle part here we'll call our X sub I because it's right in the middle. Okay, so this point right in the center, we'll call that our y sub I. Okay. So this point here, let's say the top portion is our function f of x. And this portion of our bounded area is our g of x. Okay, so two functions with respect to x. All right. So that means this point here on our graph, that's our x sub I, f of x sub I. And this point here, we'll move that over right there on the g of x graph. That's x sub I, g of x sub I. Okay. Now remember, this is just in our 2D graph. Okay. Now with the planar lamina, lamina, like I said, pronounce it how you like. We have a uniform density on this mass. Okay, that means the density throughout the entire thing is the same. Now, that's not saying that the density doesn't change. It could change right out here, or it can change as soon as you pass B. It can change below g of x or above f of x. But we know that the mass, the density, is the same when bounded in this area. Okay, so planar of uniform density that we'll call rho. Again, it looks like a lowercase p, bounded by y equals f of x, y equals g of x, and x between a and b. All right, so our formula for mass equals density times the area will give us mass is equal to the density times the area, which of course is our f of x, I minus g of x, I, delta x. Okay, so we have our density, which is our rho. We have our area, remember, which is our width, or our width times our length. Okay, so we have our width times our length, which is our delta x. All right. Okay, so if you are still writing, feel free to press pause, but we're going to continue on our next page. Okay, so now in 3 dimensions, the term lamina can be extended from just having a constant density to now having thin plates of variable density. So in other words, if it's not, instead of being constant throughout the whole thing, you can have a small area where the density is different than the area next to it, different than the area next to that, and it's different than the area next to that. Okay, so it's going to have a variable density in 3D terms. Okay, so it can be extended from having a constant density to having thin plates of variable density. Okay, now that's where the double integrals come in. We use the double integrals to find a lamina of variable density, where the density on our xy point is denoted by rho. Okay, double integrals. Help find lamina of variable density, where the density at some point xy is denoted by rho of xy. Okay, which leads us to our actual definition. Okay, that was kind of the overall explanation, but the general definition kind of goes here. Okay, so definition of mass of a planar lamina of variable density. Okay, so let's say if rho, that's just rho, is a continuous density function, on the lamina corresponding to the plane well, not say the plane, say a plane, region R, then the mass of the lamina is given by double integral of mass is equal to double integral over region rho of x, y, with respect to the area. Okay. I know you're probably thinking, why didn't you just give us that formula in the first place? Well, you have to kind of explain it. You can't just give you a formula without an explanation as to how to properly use the formula and why you're using it. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our first example. Okay, so for example, what if we wanted to find the mass of the lamina described by the inequalities x is between 0 and 4, y is between 0 and 3, with the density rho xy is equal to xy. So let me clean up that row a little bit. There we go. Alright, so to find the mass, we just find the double integral of our rho. Okay, which is equal to the integral x is between 0 and 4, and y is between 0 and 3. Our rho of xy is xy. Our area is dy dx. Alright, so just like any other double integral, we're going to start in the middle. Okay, so bringing that down here, 0 to 4, our dx will be brought down a little later. So here, our integral with respect to y, the x is treated as a constant, so it's just y squared over 2. So we have x, y squared over 2, and that's from 0 to 3, and we still bring down our dx. Okay, so remember this is just the y is equal to 0 and y is equal to 3. Okay, that's going to equal 3 squared is 9, so you have 9x over 2 minus, as soon as you plug in 0, that's just 0. So we end up with 9 over 2 x dx. Okay, so now we go ahead and integrate that. Okay, so we have x squared over 2. So that gives us 9 over 2 times 1/2, which is 4. So we have 9x squared over 4, and that's from 0 to 4. Okay, so if we plug in 4, 9 times 16 is 144 over 4, minus, if you plug in 0, it's just 0, so we don't have to do that, which is 36. Okay, so you have a mass of 36 for this problem. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Alright, so let's say, for example, we wanted to find the mass. Find the mass of the lamina described. Oh, let me clean that up a little bit. So described by the inequalities x is greater than or equal to 0, and 0 is less than or equal to y, less than or equal to the square root of 4 minus x squared, with the density of rho at xy is equal to xy. Okay, so we just use the same density as the previous one, but we changed up the inequalities. Alright, so they gave us our y boundaries, but they didn't give us the x. Okay, so what do? We have to figure out our x boundaries. We have x is greater than or equal to 0. We have 0 less than or equal to y is less than or equal to the square root of 4 minus x squared. Okay, so what does that give us? We kind of look here. We see that because that's a square root, and we're only dealing with real numbers, that means that 4 minus x squared has to be greater than or equal to 0. Okay, so if you add x squared on both sides, I'm just going to go ahead and flip it around. X squared has to be less than or equal to 4. Or you got 4 is greater than or equal to x squared. Same thing. Okay, so if we solve this, we have x is less than or equal to positive or negative 2. But since x is greater than or equal to 0, that one right there, we know that x is less than or equal to 2. Okay, so that turns this into x is between 0 and 2. Okay, remember, they don't always give you your boundaries. Sometimes you have to use your boundaries and what that they do give you and figure it out. Uh-oh, but I put a 0 there. Put an x there. There we go. All right. Okay, so now we can go ahead and start solving. Okay, so we know that our mass is equal to the integral from 0 to 2 for our x, and the integral from 0 to square root of 4 minus x squared for our y of our rho, which is xy dy dx. All right, so just like before, we start in the center. So we go from 0 to 2. So with respect to y, we have y squared over 2. So that gives us x y squared over 2. And that's from 0 to the square root of 4 minus x squared. Okay, and don't forget our dx. All right, so that's equal to our integral from 0 to 2. We have the square root of 4 minus x squared squared, because remember this is just our y is equal to 0 and y is equal there. Okay, so the square root is 4 minus x squared squared is just 4 minus x squared, because the square and the exponent are going to cancel each other out. So you have x times 4 minus x squared over 2 and our dx. All right, so we're going to go ahead and distribute that and just pull that 1/2 one out. So we're from 0 to 2, 4x minus x cubed dx is 1/2 times, we have x squared over 2, 4 divided by 2 is 2, so you have 2x squared minus x to the 4th over 4, so we have 1/4 x to the 4th, and that's from 0 to 2. Okay, so that's 1/2 times, if we plug in our 2, we have 2 times 4, which is 8, minus, if we plug in our 2 here, 2 to the 4th power is 16, 16 divided by 4 is 4, so we have 1/2 times 4, which is just 2. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and continue. Now we're going to look at moments and center of mass of a variable density planar lamina. All right, so what if we look at our XY plane, and if we have some mass in that plane. That we'll call our region. Okay, so let's say if we pick a little sub-region of it, we'll call our R sub I. And in there, you go ahead and just mark what we look at as the center. Okay, so of course, in our 2 dimensions, if this is some point y and this is some point x sub I, okay, we can see here that this is just our point that we'll call x sub I, y sub I. Okay, so from there, just from this graph, we're going to look at a new description that we'll call moments. Okay, so what if we let rho be the continuous density function on that region? Continuous density function on the planar lamina that we will call R. Now what we will call moments of mass with respect to the x and y axes okay, those will be denoted by an uppercase M with respect to x. Okay, so that's going to equal double integral of our region and y times rho of x y with respect to the area. And our moment with respect to the y-axis is equal to the double integral of x times rho of x y with respect to x. Now remember, when it's respect to x, you're going to multiply it by y. Because if you look at it, y is the distance to your actual x value. So your x-axis, sorry, I'm thinking about this one. Okay, this is actually the distance to your x-axis, and this is your distance to your y-axis. And your x is your distance to x-axis, I mean y-axis. Okay. Okay, and of course here, we already know that's your mass, so distance times your mass. Okay, now if we have our mass of the lamina, then the center of the mass is, we'll call that x bar and y bar for our center. And that's equal to our moment with respect to the y-axis divided by m, and our moment with respect to the x-axis divided by our mass. Okay. Now, if our region is a simple plane and not a lambda, then our center is just called the centroid. Okay, so we know that this is the formula for our center of mass, and these two are the formulas for our moment of mass. Okay, so of course, if our region represents a simple plane, region, and not a lambda, the point x bar, y bar is called the centroid of the region. Okay, so if you run across the term centroid, you'll know why. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our first example. Well, not our first example of moments and mass and centers and all that good stuff. All right, so let's say, for example, we want to find the mass and center of mass of the lambda for the density, say rho is equal to just k, over the rectangular region with vertices zero, zero, A0, 0B, and AB. All right. Okay, so we can see here that the x component of our ordered pair goes from 0 to a. It just kind of fluctuates between 0 and a. Okay, so we know our mass is going to equal the integral from 0 to a, and same thing with our y. We see that that just kind of fluctuates between 0 and b. So that's going to be the integral between 0 and b of our rho, which is just k, and dy dx. Okay. So again, starting at the center, that's going to equal 0 to a. With respect to y, that's just a constant times y, which would just be ky. And that's from y equals 0 to y equals b. Plug in b, you get k times b. You plug in 0, you get 0. Oh, got my dx. So that actually will give us the integral from 0 to a, kb with respect to x. Clean up that b a little. mean at K. There we go. Okay, now if we go ahead and integrate this one, we will end up with respect to x, of course, the k and the b are both considered constants. So that would just be kbx. And that's from 0 to some value a. If we plug in x equals a, because remember that's x equals 0 to x equals a. If we plug in a, we get kba. If we plug in 0, we just get 0. So we see here that our mass is equal to, we'll say, kab. Okay, so now we will look at our moment of mass, because we have to find the center. So we can only do that if we have our moments of mass. Okay, so if we find our moment of mass with respect to the x-axis, okay, we know that's equal to double integral over the region. Remember, that's y times our rho of xy. Let me kind of separate this a little bit with respect to the area. Okay, so we already know that's from 0 to a, 0 to b. So now that's y times our rho. So that would just be our rho times y. And dy dx. Okay, so just like before, we start from the middle and work our way out, which will bring us to k times y squared over 2. So the integral from 0 to a, ky squared over 2 from 0 to b. Remember, that's y equals 0 to y equals b. Okay, we plug in b, we get kb squared over 2. We plug in 0, we get 0. So that's just the integral from 0 to a, kb squared over 2 with respect to x. Okay, so we go ahead and integrate that. We get kb squared over 2, which is treated as a constant with respect to x. So that's just kb squared over 2 times x. Make that a little smaller. kb squared over 2 times x from 0 to a. Okay. Of course, we plug in our a, we get k. Well, plug in our a for x, we get ka b squared over 2. Plug in 0, we just get 0. So we get ka b squared over 2, which is our moment of mass in the x direction. Okay, so now we find our moment of mass in the direction of the y-axis, or with respect to the y-axis. Okay, and we know that's equal to the double integral over the region of x times our rho of x, y, with respect to our area. All right. So we know that's going to equal the integral from 0 to a and the integral from 0 to b. X times rho, that's just, our rho is k, so k times x. dy dx. And of course, starting in the center. Okay, so that's equal to the integral from 0 to a. So with respect to y, it's just ky, which they would consider that a constant. I mean kx, so that would be times y. So that would become kx y from y equals 0 to y equals b dx. All right. So that would equal, the integral from 0 to a, y equals b is just kxb. Plug in 0, you get 0. That's kxb with respect to x. Alright, so if we integrate this with respect to x, that's just kb times x squared over 2. And I'll make that a little bigger and just move that out to the front. So it's kb times x squared over 2, and that's from 0 to a. Okay, so you plug in a, you get ka squared b over 2. Plug in 0, you get 0. So that's ka squared b over 2. Okay, so that's our moment of mass in the direction of the y-axis. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and continue this on the next page because we are running out of room on this sheet. But we're almost done. Okay, so to find our center, we know that's the moment of mass with respect to the y-axis over our mass, okay, which is equal to ka squared b over 2 divided by kab. Okay, which if you wanted to, you can make that ka squared b over 2 times the reciprocal 1 over kab. K's cancel out, b's cancel out, and one of the a's cancel out. So you end up with a over 2. So our y bar, which is the moment of mass in the x direction over our mass, that's equal to ka b squared over 2 divided by kab, which of course if you wanted to break that down would be ka b squared over 2 times 1 over kab. Okay, so the k cancels out, the a cancels out, and one of your b's cancel out. So you get b over 2. Okay, so our center of mass is just a over 2, b over 2. Alright, so hopefully this video made sense. And this is just the first part of the applications video, so the second part will be next, and I'll see you on the next video.